Oh, in this one we're going to set up to find the region above the paraboloid z equals x squared plus y squared, and below the sphere x squared plus y squared plus z squared equals 6. And a picture might help us out. The paraboloid is the rainbow color, the hemisphere is chopped off I guess we could say is chopped off part of our paraboloid, and the volume we're seeking is this piece in between the two. Okay, I was able to draw the graph of this one in a standard way. This one I had to convert into cylindrical coordinates, but there we have the picture. And to get the region R, we could see that it's a circle centered at the origin in the xy plane, but it's hard to figure out what the rest of it would be. But the radius we can find by solving the system of equations, substituting z equals x squared plus y squared into our sphere equation. So z replaces x squared plus y squared, so we got z squared plus z minus 6 equals 0. So z plus 3 times z minus 2 equals 0 if it's factored, so z equals 2 is a positive solution. So z equals 2, substituting that back into here, we get z squared equal to 4, so x squared plus y squared plus 4 equals 6. And we have the circle x squared plus y squared plus z squared equals 2, the square root of 2. So our region R is x squared plus y squared is less than or equal to 2. So now we've got our region R, and looking down, circle of radius square root of 2, looking straight down on this birdie, from negative square root of 2 here to positive square root of 2 here in x direction, and it's a circle of radius square root of 2, so that should give us our y limits pretty easily. And so here's the bottom, z going from x squared plus y squared to the top. This is the upper part of the hemisphere, or actually the upper hemisphere of the sphere I've drawn there, and integrating with respect to z first, and then y, since it's a semicircle, from negative square root of 2 minus x squared to positive square root of 2 minus x squared, and x going from negative square root of 2 to positive square root of 2. So I think in order to compute this, it would be good to switch to polar coordinates after the first integration. The first one's easy enough because we're just going to get z going from here to here, and as you can see when we evaluate that, we're going to get square root of 6 minus z squared minus y squared minus x squared plus y squared. Z, and y going from here to here is x going from here to here still. But I think from this point we'd want to switch to polar because the x squared plus y squared is very convenient. It happens here, and change that to r squared. But more importantly, this x squared plus y squared just turns into this r squared, and we can integrate by a u substitution because of the r dr d theta that's outside the square root. And so I just use this to evaluate without too much trouble. I used my software to evaluate and got this answer: 4 square roots of 6 pi minus 22/3 pi. Of course, then approximately what would that be? By the way, making this u substitution, it turns out to be pretty nice because part of the integral is necessary for that to get the square root of 6 minus r squared, and you can probably figure where most of that came from. And I guess I could do an approximation. What is the volume approximately? And about 7 3/4 cubic units, whatever that may be, is the volume of this unusual shaped piece that looks a little bit like a birdie if you're a badminton player.